It's only when you have a mismatch between the two that you need to worry about it. So our enthalpy, we're going to express using delta H, and it's determined using the formula delta H is equal to E plus P times V. So our enthalpy is going to be related to the energy of the system, the pressure, and the volume. So our enthalpy is a state function whose value depends only on the current state of the system and not the path taken to arrive at that state. So a lot of these things that we're going to see are going to be delta functions or state functions. They're all going to have a little delta in front, right? And that just means final minus initial, or products minus reactants. So what's the enthalpy or the energy of my products minus the enthalpy of my reactants? Right, so if we look at some of these chemical and physical changes, right, we can give them names. So if I'm going from a solid to a liquid, that process will give it a special name and call it the enthalpy or the heat of fusion. And if we go from a liquid to a vapor, so we're going from a liquid to a gas phase, we'll call that delta H sub vap, and that's our enthalpy of vaporization. If we go from our solid directly up into a vapor, right, that's going to, like dry ice would do, that's going to be the enthalpy of sublimation. Right? And we'll see that that's the sum of the enthalpy of fusion and the enthalpy of vaporization. Okay. So let's consider a process carried out under constant pressure where only pressure volume work is allowed. Under the above mentioned conditions, the expression delta E is equal to Q plus W becomes delta E is equal to Q minus PdV, or our Q, or heat at constant pressure, is equal to our energy change plus PdV. So we can relate our constant pressure Q to a change in enthalpy. So our definition of enthalpy will be that minus H is equal to E, our energy, plus pressure times volume. So a change in H is going to be related to the change in energy plus our PdV work change. So our delta H is equal to delta E plus PdV. So, but pressure is constant. So a change in PV is going to be caused by a change in volume. So our delta PV is going to be equal to P delta V, and our delta H is going to be delta E plus PdV. So a process carried out under a constant pressure, and where only work is allowed is a volume change, Q is going to be equal to delta H. Right? So went through a lot of stuff there, right? But what we're getting to is delta H, our enthalpy change, is only going to be related to Q if we're operating under the set of circumstances where our pressure is constant. So like in a lab where we've got an open container, right? So our closed container where you're going to, allow pressure to build up, right? We've got that cork sealed into it. That's going to be different, right? But we're not going to change the volume in that case. So in a where we've got a constant pressure, right, where only the volume change is allowed to happen because pressure is constant, we're going to like drop that term out, and so it's going to be delta H is equal to Q. Right? So under our constant pressure, delta H of a system is equal to the energy flow as heat. Right? So this is an important concept. The heat of reaction and the change in enthalpy are used interchangeably for reactions under constant pressure. So most of the time when we're working in lab, we're going to be working in a container that we're not building a bomb for, and we'll talk about bomb calorimeters, and we'll do bomb calorimetry if you take physical chemistry with me. But if we're allowing that to happen under constant pressure, say 1 atmosphere, our heat of reaction and our enthalpy can be used interchangeably. Our change in enthalpy is given by the equation. Delta H is equal to the enthalpy of the products minus the enthalpy of the reactants. Right, so final minus initial, delta H is positive when the enthalpy of the product is greater than that of the reactants, and in a reverse situation when delta H is negative. So this is just getting back to that endothermic and exothermic process. Right, so here is our exothermic process. Right, delta H is going to be negative because the energy of our products is lower than the energy of our reactants, and vice versa for your endothermic reactions. We can also view heat as a product or a reactant in a given chemical reaction. So here we've got the combustion of propane to form carbon dioxide and water. And we also have to specify the states here. So if I'm going from combustion of propane gas and oxygen gas to give me carbon dioxide and gas phase water, that's going to be exothermic to minus 2,044 kilojoules. If I am looking at the change to liquid water, I'm going to take my propane and my oxygen, I'm going to get CO2 gas, and for liquid waters, it's minus 2,220 kilojoules. Why is this number of larger magnitude? Well, in order for me to go to the gas phase to the liquid phase, I needed to remove even more heat and needed to become even more exothermic, so that's why this guy is a larger magnitude number. Sometimes you will see things with the thermodynamic standard state. It's going to give this little naught symbol up here, a little zero. That's going to represent the most stable form of a substance at 1 atmosphere in pressure and at a specified temperature, which we're going to call 25 degrees Celsius, and 1 molar concentrations for all substances in solution. So we're going to see standard state stuff a lot. And so under those conditions, we would actually call it delta H naught for this converting into the gas, and that would be our delta H naught because it kind of wants to be in the gas phase under those circumstances. All right, so other reactions are going to have different values. So aluminum reacting with iron oxide to form iron and aluminum oxide. This is a redox process. For those of you who are pyromaniacs, you might recognize this as the thermite reaction. Right, so this guy's going to give you minus 852 kilojoules per mole. And so if this sign is negative, it is exothermic. Enthalpy is flowing from the system to the surroundings. Exothermic exits the system. If you have barium hydroxide, .8H2O, so it's an octahydrate version of barium hydroxide, and you let that react with ammonium chloride, you're going to form barium chloride and 2 ammonia and 10 water, and you're going to end up with a positive change in enthalpies. Your delta H naught will be plus 80.3 kilojoules. So this is going to get colder. I'll get colder. And that's not necessarily the reaction used in cold packs, but it's close to it, like those instant cold packs. I don't think they've got a barium hydroxide. I think they might have another hydroxide in there, just because barium is not really good for you or the environment. These guys here that are negative, right? This thermite reaction is that thing's going to get hot. Right, so you can tell if something gets hotter, right, it's going to have energy exiting the system. Right, endo goes into the system. That's about the best I got for mnemonic. But if you know what exothermic is, and you know that endothermic is the other one, exothermic gets hot, endothermic is the one that gets cold. Right? We've got a couple of other subscripts or specialized cases that we can use, just like we saw the enthalpy of vaporization and the enthalpy of fusion. We've got a heat of combustion, and that's just saying I'm doing a combustion reaction. If I take two things and I combine them together, we're going to call that enthalpy or heat of formation. We'll give it a little subscript F here, right? Or we could have a heat of fusion, right? So that's where you're going from sodium chloride solid and you're melting it into sodium chloride liquid. The word confused, right? So if you're talking about confusion, that literally means that you are melting things and mixing them together, right? So if you think about taking molten silver and molten gold and you mix them together, you have melted and confused them together, and it's very hard to unmix them. Heat of vaporization is just going from the liquid phase to a gas phase. You could write any one of these as delta H Rxn for delta H of reaction, or sometimes you just say, hey, we're going to call it delta H. They're all just kind of delta H. They have these little subscripts on here to help you as the reader figure out, well, what kind of reaction are we looking at? Is it a combustion reaction? Is it a formation reaction? Are we heating something? Are we melting? So let's get a summary of the relationship between the amount in moles of a substance and the heat in kilojoules transferred during a reaction. So if you've got an amount of compound A, right, in moles, we can figure out the amount of compound B in moles, right? We're going to get that from our balanced chemical equation, right? And then we can figure out the amount of heat gained or lost in that reaction using our enthalpy of reaction in terms of kilojoules per mole. Right? So our delta H, right, you will see that as kilojoules, should usually be in kilojoules per mole because we're often times talking about, well, how much stuff do I have? And you're talking about it on a mole basis and not an individual molecule basis. And sometimes, sometimes the book is sloppy and they will leave out the kilojoules per mole when they should really have it in there for a heat of reaction. But if you're talking about the amount of heat, you're going to take the heat of reaction, kilojoules per mole, and then however many moles you've got of your stuff, and you're going to multiply them together. So delta H reaction times N, the number of moles, is going to give you your heat in joules. Well, kilojoules in that case. Something else you will also see next semester is going to be these things called heating curves. I'm bringing them up a little bit early so that you can see that this is going to be something you will need to see again. So if you're talking about going from and these heating curves are like, as I apply heat, right, what is happening to the state of matter and the temperature? So as you put something into solid ice, you can go from like minus 10 degrees, and you're going to heat it up, and then you're going to reach the point where you undergo a phase change at 0 degrees, and your solid melts. And in this process here, this melting process, you're going to use your enthalpy of fusion, right? And then you'll get liquid water, and you'll heat that up. We're going to find that's going to be related to the specific heat. So the specific heat. Right? And then you have this big long process where you've got the water that is boiling into steam, and here you're going to use your delta H vaporization. Right? So the flat parts, you're going to be using your delta H's, and on these angled parts here, that's going to be related to the specific heat of each of those materials. Specific hat. That'd be cool. All right, so let's look at an example. I got 1 mole of methane. It's burned at constant pressure. 890 kilojoules of energy is released. As heat, calculate delta H for a process in which 5.8 gram sample of methane is burned at constant pressure. Okay? So in order to do this, we're going to need to break this guy down into a couple of steps. Right? They didn't give us all the things, but some of our variables are going to be in there hiding. Right? So our general plan, right, is going to be, I'm going to take my moles, right, and I'm going to figure out I'm going to go from grams. I'll figure out how many moles I've got. I'm going to go from the moles of my reaction into heat or energy, right, or our enthalpy. Right? So in order to do that, I'm going to need, obviously, my molecular mass or molar mass to go from grams into moles, but I'm also going to need my delta H of reaction to go from moles of substance into the heat released, right? And so, just like they're going to hide our molar mass in this formula, here they've got 1 mole and so many kilojoules. We need to do an extra step to kind of figure this thing out, okay? So first thing we've got to do is we're going to calculate. So our overall objective is to calculate the enthalpy change in that particular reaction for that mass. So our information available is our Q, or our delta H, is minus 890 kilojoules per mole of CH4. We've got a mass of CH4, and we got a molar mass of our CH4. So to determine the number of moles that we actually burned, we're going to take our 5.8 grams, divide by the molar mass, and we'll get 0.36 moles of CH3. So here we're using our molar mass as our conversion factor. Right. Now that we've got moles of CH3, we're going to take our moles of CH4, and we're going to use our enthalpy of reaction, or delta H reaction, to give us the energy change for that 5.8 grams. So our moles of CH4 cancel out. Our enthalpy of reaction is in kilojoules per mole. We end up with kilojoules at the end. So our heat flow is going to be minus 320 kilojoules. Sometimes it is easier just to work with the magnitude, right, and then figure out the sign of the heat flow at the end. Right? So we did it right here, right? We followed all the rules, and we know that this guy's starting off at minus 890 kilojoules. But if you're uncertain, sometimes you can just do all the math, and then at the end, kind of think about it and say, well, if I'm doing combustion of methane, I've seen propane and butane getting burned before, and methane's going to burn, and then that process is going to release heat. I need to make sure I've got a minus sign on my enthalpy over here.